ChatGPT, Claude, Gemini, and DeepSeek look like they understand language, but under the hood they are doing something much simpler, turning text into numbers, letting tokens pay attention to each other, and predicting the next token. And the architecture that makes this possible is the transformer, one of the core engines behind modern AI. In this video, we'll open it up step by step. To understand transformers, we need to start with the core task modern language models are trained for: next token prediction. Give the model a sentence like, "The cat sat on the," and the model tries to predict what comes next. Maybe Matt gets a high probability, maybe chair gets a smaller probability, maybe sky or 7 gets almost no probability. That is the core loop. Given the context so far, predict the next token. Append it to the text, run the model again, then predict the next one. One token at a time. That simple loop is how a language model writes paragraphs, answers questions, and carries a conversation. The task is simple to describe, but extremely hard to do well. To make a good prediction, the model needs grammar, meaning context, relationships between words, and sometimes even the intent behind the sentence. So the real challenge is not just predicting the next token, it is building a rich representation of the context, one that captures grammar, meaning, relationships, and intent. The transformer does this by letting tokens exchange information with each other, layer by layer. The richer that representation becomes, the better the next prediction gets. Now let's see how that happens inside the transformer architecture. Before we zoom into each component, let's first look at the whole pipeline. First, raw text goes in. The sentence is passed through a tokenizer which breaks it into tokens. Those tokens are mapped to token IDs, numbers from the model's vocabulary. Then each token ID is used to look up an embedding vector, a learned representation of that token. At this point, the model is no longer working with raw text. It is working with vectors. Next, we add positional information because the model needs to know where each token appears in the sequence. Now the model has a sequence of vectors that carry both token information and position. That sequence passes through a stack of transformer blocks. Inside each block, two major things happen. First, attention lets tokens exchange information with each other. Then, a feed-forward network transforms each token representation. These blocks are repeated many times. Layer by layer, the model builds richer representations of the text. At the top, the final hidden states are projected back into the vocabulary. The model produces a score for every possible next token. Softmax turns those scores into probabilities. Then one token is selected. That token is appended to the context, and the model runs again. Raw text goes in, token probabilities come out, and token by token, the response is built. The first step is tokenization. A model does not read text the way humans do. It does not directly see words, sentences, or paragraphs. It sees tokens. A token can be a whole word, part of a word, punctuation, or even a space pattern. For example, a common word like cat might be one token, but a less common word like unbelievable might become multiple tokens, something like un, believe, and able. This is useful because the model can represent many words using a smaller set of reusable pieces. Instead, it uses a vocabulary of reusable text pieces. Once the text is split into tokens, each token is mapped to an ID. So the sentence becomes a sequence of numbers, something like the becomes 791, cat becomes 8415, sat becomes 10139. The exact numbers do not matter. What matters is this: text has been converted into a format the model can process. But these token IDs are still just labels. They do not carry meaning by themselves. That is where embeddings come in. Each token ID is used to look up an embedding vector. An embedding vector is a long list of learned numbers. It is the model's first internal representation of that token, before context is added. Tokens that are used in similar ways tend to have similar embeddings. For example, cat, dog, and kitten may end up closer together in this vector space. Words like Tuesday, airplane, or 7 may live somewhere else. This does not mean the model understands words like a human, but it gives the model a mathematical way to represent similarity, usage, and relationships between tokens. So after tokenization, every token becomes a vector. Now the sentence is no longer just a row of IDs. It is a row of embedding vectors, each representing a token. But embeddings alone are not enough. They only give the model an initial representation of what each token is. but not where it appears. And position changes meaning. Dog bites man, and man bites dog. Same tokens, different order, completely different meaning. So before the transformer can process the sentence properly, it needs one more thing: positional information. This gives each token a signal that says, I am first, I am second, I am third, and so on. In practice, positional information can be added in different ways. Some models use positional encodings, some use learned position embeddings, some use newer methods like rotary position embeddings. But the basic idea is the same. The model needs to know not only what each token is, but where it appears in the sequence. The token embedding represents the token itself. The positional information represents its place in the sequence. Once positional information is included, the model has a sequence of vectors that carry both token information and order. Now we can send them into the transformer blocks. A transformer is built from repeated blocks. You can imagine one block as a processing layer. Each block takes in a sequence of token vectors and outputs a new sequence of token vectors. The number of tokens stays the same, but each vector becomes more informed by the context around it. Inside each block, there are two main operations. First, self-attention. This is where tokens exchange information. Each token looks at other tokens and decides which ones matter most. Second, a feed-forward network. This transforms each token's vector individually after attention has mixed in context. These two parts are wrapped with residual connections and normalization, which help deep neural networks train reliably. Modern LLMs stack many of these blocks. Dozens of layers, sometimes more. Each layer refines the representation. In the early layers, the vectors mostly represent the tokens themselves. In the later layers, they represent tokens in context. That contextual representation is what makes the model powerful, and the core mechanism that builds it is self-attention. Self-attention is the heart of the transformer. The idea is simple. Each token looks at other tokens and asks, which ones matter most to me? Take this sentence. The cat sat on the mat because it was tired. What does it refer to? A human reads this instantly. It means the cat, not the mat, because a mat cannot be tired. But the model does not start with that understanding. To connect it back to cat, the model needs to look across the sentence and decide which ones it is really about. That is exactly what self-attention does. For each token, the model creates three vectors: a query, a key, and a value. Think of the query as a question. The token it is asking, which earlier word do I refer to? The key is a label each token carries, describing what it can offer. For example, cat carries a key that signals, I'm an animal, I'm the subject of this sentence. The model compares the query of it against the key of every other token. The token whose key fits best gets the most attention. The value is what actually gets passed along. Once it locks onto cat, the meaning of cat flows into it. So the query asks, the key answers, and the value is what gets shared. To decide how much one token should pay attention to another, the model compares the query of one token with the keys of the others. A strong match means high attention. A weak match means low attention. Then the model uses those attention scores to blend the value vectors together. The result is a new version of the token vector, enriched with context from other relevant tokens. The word is still it, but its vector has changed. It no longer represents a bare pronoun, it now carries the meaning of cat inside it. That is what attention does. It turns isolated tokens into contextual tokens. So far, we've described attention in words. Now let's see what it actually looks like as a grid of scores, the way the model computes it inside. For every token, the model computes how much it should attend to every other allowed token. These scores form an attention matrix. Rows represent the token doing the looking. Columns represent the tokens being looked at. Each cell says, how much should this token pay attention to that token? For example, in the sentence, the cat sat on the mat, the token cat may pay strong attention to sat because that tells us what the cat did. It may also pay attention to mat because that helps complete the scene. The brighter the cell, the stronger the attention. But raw scores are not enough. The model applies softmax, which turns them into weights that add up to 1. Then the model takes a weighted sum of the value vectors. So the output for each token becomes a blend of the most relevant information. That is why attention is powerful. It is not just matching words, it is dynamically deciding which relationships matter in this specific context. There is one important detail for modern language models. During training, the model is shown the entire sentence at once. All the tokens are present in the input, including the ones it is supposed to predict. That creates a problem. When the model learns to predict the next token, it must not peek at the tokens that come after it. Otherwise, it would just copy the answer instead of learning to predict it. So, when predicting the word after, the cat sat on the model should only look at the, cat, sat, on, and the. It must not look ahead to the token that comes next. So, decoder-only language models use causal attention. This means each token can only attend to itself and previous tokens, not future tokens. This is done with a mask. The mask blocks attention to future positions. That is why these models generate from left to right. They build one token at a time, always using only the context that came before. This is also where modern LLMs differ from the original transformer. The original transformer had two parts, an encoder and a decoder. The encoder read the whole input at once and the decoder generated the output. But most modern LLMs keep only the decoder. They are built for one job: look at the previous tokens and predict the next one. One attention pattern is useful, but language has many kinds of relationships. Some relationships are grammatical, some are semantic, some track position, some connect pronouns to nouns, some connect a verb to its subject, some connect a question to the part of the context that answers it. So transformers don't rely on a single attention pattern, they use multi-head attention. Instead of paying attention just once, the model runs several attention operations side by side in parallel. Each head gets its own learned projections for queries, keys, and values. That means each head can learn to focus on a different pattern. One head might focus on nearby words. Another might track long-range dependencies. Another might connect objects to actions. Another might follow punctuation or structure. After all heads finish, their outputs are combined back into one vector. So multi-head attention gives the model multiple views of the same sequence. Not one relationship map, many relationship maps, combined into a richer representation. This is one reason transformers are so effective at modeling language. But attention is only half of each transformer block. In part 2, we'll build the other half and follow the whole process all the way to an actual predicted word. That's it for today. Like and subscribe so you don't miss out on more AI deep dives. See you in the next one.